Welcome to lecture 2.2 in the unit on basic definitions and concepts of the course on introduction to TFA and wavelet transforms. In the introductory lecture and subsequently we have used terms such as energy density, power spectral density, energy and power and so on. There we have used the terms loosely, but it is time to learn these terms in a more formal framework. So, the objective of this module is essentially that we will formally learn what are power and energy signals. In fact, it is just a review of these concepts. These are supposed to be known before even we dwell into time frequency analysis. And these energy densities are defined in time, but when we move to frequency domain, particularly for discrete time signals, but one can strike densities may not exist in the time domain for discrete time signals, but densities exist in the frequency domain. And one can show that these densities in frequency domain are related to what are known as covariance functions. Again, these are concepts that are taught in a typical second year or a third year signal processing course, but we will review for the benefit of everyone and discuss two measures known as the cross covariance function and autocovariance functions, again for deterministic signals, which is the framework for this course. So, let us begin with the definition of an energy signal, and for that we need to define what is energy. The definitions for the continuous time and discrete time signals are shown here in equation 1. Obviously, continuous time signals involve an integral and discrete time signals involve a summation. Essentially, these definitions come from electrical engineering and physics. The definition is fairly straightforward. It's assumed that when these definitions originally assumed that the measurements or the signals are electrical quantities and therefore energies are defined in this manner. And you also notice that there is a modulus square rather than simply x square, that is essentially to accommodate complex valued representations. In fact, we will come across this complex valued representations shortly in the next module and subsequently as well throughout the course. So, the energy of a signal has to be understood as the energy expended by the process to generate the signal, and we evaluate it over the entire existence of time. When a signal has finite energy, continuous or discrete, we say that it is an energy signal, and number of examples can be given. All finite duration and finite amplitude signals have finite energy. So, an example is an exponentially decaying signal. Of course, that does not have a finite duration, but it is exponentially decaying. You can show it has finite energy, but otherwise all finite length signals have finite energy and therefore they are energy signals. On the contrary, a periodic signal exists forever and it has infinite energy, therefore it is not an energy signal. Accompanying this definition is the notion of this power signal. Again, the definition of power is inspired from electrical engineering and physics. Strictly speaking, this is the average power. As you can see from the definition, it is defined in a limiting sense over the entire existence of the periodic signal. Here capital T for the continuous time signal refers to the periodicity, and capital N, or you can say 2n plus 1 is the periodicity of the period of the discrete time sequence signal. Again, here these are average definitions for both continuous time and discrete time sequence signals. If a signal has finite power, then we say that the signal is a power signal. And we just mentioned earlier, periodic signals have infinite energy, but have finite power. The interpretation of power is once again on the same lines as energy. It is the rate at which the system that is producing, the system is putting in, rate at which the system is expending the energy to produce these signals. Always remember that no signal exists without a system. So, whatever properties we derive of a signal, actually what we are doing is we are referring to the system that is generating the signal. This system could be a man-made system or a natural system, but it is a device or a system that is generating this signal. The random signals also are power signals because by definition random signals are assumed to exist forever and they never decay, and therefore they have infinite energy and also they have finite power. In general, any signal can either be a power or an energy signal, but there are also exist classes of signals which are neither finite energy or power signals. They may have infinite power and infinite energy, but we shall not talk about this. In practice, you either run into power or energy signals and so on. Having said this, I should tell you that all the observed data, because since all the observed data are collected over a finite time, and therefore over that finite time the signal has finite energy and the average power is 0. Why should an energy signal have 0 power? Because the moment I say a signal is an energy signal, it exists for a finite time or its energy is finite, whereas average power is the energy spent over the entire time of its existence. When you and because the average power is defined in a limiting sense, all energy signals will have 0 power and so on. Okay. So, you have to be comfortable with these definitions, and you have to be clear in your mind whenever you are using the term energy spectral density and power spectral density and so on. You have to recall these definitions until you are really comfortable with it. Okay. So, associated with the energy definition, if I can take you back to the definition of energy, you can observe in this integral here in the equation 1 that the energy is the area under a curve which is modulus x of t square. So, drawing analogies with mechanics and probability density functions and so on, we can treat modulus x t square as an energy density. So, that the area under this density curve gives me the total energy. Right. So, that is the idea, and we extend this notion somewhat to the discrete time signal, although it is not an area, but in a discrete sense it is an area. So, it is a loose interpretation there. So, here we have now what is known as the energy density in time. Slowly one should get comfortable in time frequency analysis with energy densities in different domains. This is energy density in time. Shortly, in the sense in a few modules from now, we will also speak of energy densities in frequency domain. Every time we talk of densities, we should ask if they exist. So, for the continuous time case, if it is an energy signal, the energy density exists, and I am showing you an example here of a Gaussian modulated signal, which of course, if you can see from the plot, it exists for a finite time, it decays, but it decays to 0, and what you see on the right is the energy density. Just to give you a feel, these energy densities are later on used in deriving what are known as duration, defining duration and bandwidth and so on. The energy density in frequency will allow us to define the bandwidth. Loosely speaking, you can interpret this energy density as an instantaneous power, but I do not really advocate that advocate that definition for a long period of time. It is just a loose interpretation. Along the lines of energy density, one can define power density. Again, I will take you back to the definition of power density. If you look at this equation 2 here, what you can see is the modulus x t square, strictly speaking, should be by 2t, but you can always define by t. The area under that actually gives you the power, and therefore, I can treat modulus x t square by t, where t is the period of the signal, as the power density in time. Again, this is an average power density in time. And for both for the discrete time case, both the energy and power densities in time do not exist, and the reason is here. If you look at it, the densities are only applicable to a continuum. This is what exactly I said earlier. You can only think of modulus x k square in a loose term as a density, but strictly speaking, it is not a density. However, we can think of distributions, and here if you have some random variables or probability theory, recall that the probability density function exists only for continuous valued random variables, and they does not exist for discrete valued random variables, whereas in both cases the notion of a probability distribution exists. Okay, that is valid. Likewise here, for discrete time signals, you cannot talk of a density simply because in discrete time, time is not a continuum. You only have discrete points. However, you can have densities of energy and power in a transform domain, and here we are hinting at frequency domain, Fourier domain and so on. And we will learn shortly that these energy and power densities do exist for discrete time signals in frequency domain. That is what we call as energy spectral density and power spectral density and so on. Assuming of course that the energy and power are defined accordingly. Now, as I mentioned early on in this module, these energy and power spectral densities are very closely related to what are known as covariance functions. So, now we are moving from the univariate world momentarily to a bivariate world. What I mean by bivariate is two signals. So, let us begin with this very familiar measure called cross covariance function. This cross covariance function is actually a measure of linear dependence between two signals that are shifted in time. In the sense, what you do is you take signal x and signal y, these are the two signals. I shift one of them with respect to the other by a certain amount L and measure the covariance between them at that lag L. When I evaluate this covariance between this x and shifted y or y and shifted x at different values of L, I get what is known as a cross covariance function. I will give you the definition shortly. What is very important to remember is that this cross covariance function is a measure of linear dependence, and this is used widely in testing linearity and so on. If you actually do a search for covariance, literature search, or if you read any books on covariance and so on, typically you will see this covariance is defined in a statistical sense, that is in the context of random variables, and also cross covariance functions are defined for random signals. But here we are going to review the definitions for deterministic signals. Cross covariance is a concept. It is a concept that asks how two signals are varying together. That is why it is called the cross covariance. You can apply this to deterministic as well as random signals. And here what we are going to do is we are going to look at the deterministic case, and normally this cross covariance is normalized to get cross correlation function so as to make it independent of the choice of units. So, if I am relating temperature and pressure of a gas, or if I am relating voltage and current in a circuit or in a wire, then the units will make a big difference to the value of the cross covariance that you are evaluating. You want a measure that is invariant to the choice of units, and that is one of the reasons why we choose to work with cross correlation functions. And I want to caution the viewer here that these terms cross covariance and cross correlation are used slightly differently in statistics and in signal processing. The term that I am using here is from a statistical perspective, cross covariance. If you turn to a signal processing text, the cross covariance function is replaced by a term called cross correlation, which is actually normalized cross covariance for statisticians. Okay. So, without confusing you further, cross covariance and cross correlation in statistics mean cross correlation and normalized cross correlation in signal processing. So, you have to be careful with the terminology that you are using, and a lot of times if you turn to statistics, I'll talk about with respect to this definition here. So, this is the definition of the cross covariance for periodic signals. You look at this definition given here in this equation, you can see that we are evaluating this cross covariance over the period of the signal, because this definition is for periodic signals. Notice that the subscript is sigma xy. This is the notation that we are going to use, and as I said earlier, the notation is such that for discrete time sequences or signals we use a square bracket to keep track of the index. So, sigma xy at L for a periodic signal is given as a time averaged summation, time averaged product of x y, but not just plain x y, but x y k minus L. So, that is the shift that I was earlier referring to. In statistics, if you turn to this definition of cross covariance function, you would see that the means are subtracted from the respective signals, whereas for deterministic signals we do not, and that is one of the prime differences that you should keep in mind. In MATLAB there are two different commands called XCOV and XCORR. XCOV subtracts means from the respective signals before computing the cross covariance, whereas XCORR does not. So, in a sense XCOV is to appeal to the statistical community and appeals the statistical community, and XCORR is meant for signal processing, but if you know what you are doing you can use either of these functions, it is not a big problem. So, this cross covariance function for periodic signals is evaluated only over the period, that is something that you should observe, and what you see here is a cross correlation as I mentioned earlier, it is a normalized cross covariance. The normalization factor as you see in the denominator is a square root of product of two terms, which is sigma xx at lag 0 and sigma yy at lag 0. It is xp, but I am ignoring the subscript. So, what is the sigma xx of 0 and sigma yy of 0? These are autocovariances evaluated at lag 0, which I will talk about shortly. Okay. Now, it is easy to see by setting x equals y and evaluating this cross covariance at lag 0 gives me the average power of the periodic signal, if you go back to the definition. Now, the cross covariance for aperiodic signals is naturally defined over the entire existence of the signal. Now, the summation runs from minus infinity to infinity as you can see, but the form of the expression does not change significantly. There is no averaging in the sense here, because the existence is in principle over the infinite time, whereas for a periodic signal you average it over a period. The rest of the things carry forward. The cross correlation again here is a normalized cross covariance, and when you set x equals y and evaluate it at lag 0, you recover the energy of that particular aperiodic signal. Again, this definition of cross covariance only holds if the signal is aperiodic and has finite energy. You can have an aperiodic signal, that means it has no period, but has infinite energy. A classic example of that is a sine square root 2 times k. Okay. So, if I look at a signal sine root 2 k, this is a discrete time sine wave, but it is not periodic. The reason is the frequency is irrational. We recall the discussion that we had in the previous module. This has infinite energy, but it is not periodic, and therefore, you cannot apply this definition of cross covariance that you see in the expression. Okay. Now, the cross covariance function has a number of useful properties, or a few but very useful properties, and is perhaps one of the most widely used tools in signal analysis. It is used in delay estimation, it is used in impulse response estimation and so on. So, I list some of the important properties here. As I mentioned earlier, the cross covariance measures the linear dependence between two signals that are with one of them shifted with respect to the other, and therefore, it is used in testing linearity, the linear dependence between two signals. If you think of x as input and y as output, then you can use this cross covariance function to see if you can develop a linear model between the input and output of a given system. And it is an asymmetric measure, that is a very important property of the cross covariance function, which means sigma xy at lag L is not the same as sigma xy at minus L. And this should be expected, because you cannot expect x to affect yk minus L. That is, assume that L is greater than 0, then sigma xy at lag L is examining the dependence or influence of yk minus L, a past value of y on a current value of x. That need not be the same as how a future value of y is related to the present value of x, particularly if you think of x and y as input and output or of a causal system. So, naturally it is an asymmetric function. However, autocovariance, as we learn later on, is a symmetric measure. Now, there is another word of caution that I want to mention here, make here. We have used the definitions as xk, I mean sigma xk yk minus L, and likewise for a periodic signal. In many texts, you may see xk yk plus L. So, you have to be careful There is nothing wrong with that definition either, but then you have to be consistent with the rest of the development and the way you interpret the cross covariance and so on. And particularly when you are using a software package, you should make sure that you refer to the documentation to see what definition one is using. Okay. And thirdly, the cross covariance function specializes to the autocovariance function for univariate signals, as I mentioned earlier. And this autocovariance function has a number of useful properties and so on. That is the last item that we are going to discuss in this module. And I mentioned earlier that in MATLAB there are two commands, XCOV and XCORR. I would like you to go and look up the help or the documentation on these commands. You will see that XCOV computes a cross covariance by mean centering, that is by first removing the means from the respective signals, whereas XCORR does not remove the means. But if you know what you are doing, you can actually produce the same results. And there are other options in XCOV and XCORR. For example, you can get normalized coefficients, which means you can get cross correlation, or unnormalized, which is cross covariance. So, check out the help on these two routines. Fine. So, let us quickly now move on to autocovariance function. This is nothing but the cross covariance function evaluated for the same signal. So, this is not a new definition in itself. It is actually obtained by setting x equals y in the respective definitions for periodic and aperiodic signals. And as I mentioned earlier, unlike the cross covariance function, the ACVF is a symmetric function. Autocovariance function is a symmetric function. Therefore, you will see in all the texts, the autocovariance functions are plotted only for the non-negative set of lags. And the normalized versions again give rise to what are known as autocorrelation functions and so on. The main property of this autocorrelation function is that it inherits the characteristics of the signal. Okay. What it means is, suppose a signal is periodic, then you will actually see periodicity in the autocorrelation or the autocovariance function as well. Let me drive home this point by means of these two examples. The first example on the top that you see is for the case of a periodic signal. On the left here you see the mathematical result. This is easy to show. I leave that as a simple exercise to you. If x is a cosine or a sine, then sigma xx, which is the autocovariance at lag L, is also a periodic signal with the same period. And what you see on the right is an illustration of this result, where I have chosen the period to be 20 samples. And I am plotting the autocovariance, not the autocorrelation. The way to find out if it is autocorrelation or not is to check the value at lag 0. If at the lag 0, if the value is 1, then most likely it is an autocorrelation that is being plotted, because at lag 0 you are measuring the similarity of the signal with itself, and that obviously has to be 1, and that is how the autocorrelation is defined. For the aperiodic case, again here I show for the case of an exponentially decaying signal, and I have derived the expression for the autocovariance function. Again I leave that as an exercise to you to derive the expression, and I am showing the results for alpha equals minus 0.05, and once again you can see that the autocovariance has inherited the properties of the signal. Now you may ask, what is the big deal about this? I mean, whatever the signal has, the autocovariance is showing that. So I can extract the features, the same features from the signal. Why do I need to work with autocovariances? Well, the answer to that is, if I have a signal with noise, I do not show that here, but at an appropriate moment I will show you that example. If, let us take the top example, the periodic signal here. If this periodic signal was corrupted with some mild amount of noise, then it would not be easy for you to observe the periodicity by a direct visual inspection of the time domain signal. Whereas, if you plot the autocovariance function of this corrupted sine wave, then it retains its periodicity because of the properties of the noise, and I am particularly referring to a kind of noise here. If you add uncorrelated noise, which is white noise, then what happens is the property of white noise is such that its autocorrelation is 0 at all non-zero lags and 1 at lag 0 by definition, which means the noise affects the signal at every point in time, but in the lag domain the noise affects the ACVF only at lag 0, and theoretically it does not affect the autocovariance of the measurement at any other lag. So, therefore, the periodicity is revealed in a more significant way in the autocovariance domain or the lag domain and so on. So, that is one of the key properties of ACVF that is exploited in periodicity detection. Okay. So, with this I want to conclude this module, and of course, I want to also make a few remarks. We have actually defined covariance functions here for deterministic signals, but as I mentioned, you can apply this to signals which are corrupted with noise without much abuse of these definitions. More importantly, the definitions of covariance functions also exist for stochastic signals. In fact, mostly you will find the definitions introduced for stochastic functions everywhere, stochastic signals everywhere, and for you will find very relatively few definitions for deterministic signals being cited. But the stochastic signals definitions involve ensemble averages, that is averages across all realizations instead of time averages as we have done for deterministic signals, and these ensemble averages are evaluated by what are known as expectations. And finally, what I want to make a point is with regards to the use of ACVF for periodicity detection. I mentioned earlier that it is a very useful tool for periodicity detection, but a much better tool is a spectral density, particularly when you have more than one oscillatory component in the signal. I showed you earlier the example where there is a single oscillatory component. Theoretically, ACVF is periodic, allows you to detect periodicities even if you have multiple components, but the practical utility of that becomes low, whereas the spectral density is excellent at doing that. Of course, when we move on to the third unit on the review of Fourier transforms, we will know the definitions of spectral density. So, here are a few references for your perusal. In the next module, that is 2.3, we will learn a few more basic definitions and concepts on signal representations and dot products and projections and so on, which will then set the platform for the review of Fourier transforms. Thank you.